My name is Frank Longford, and for my fellowship, I worked with Forensic Architecture, a research agency that perform open source investigations. Now, contemporary conflicts tend to be occurring in heavily populated areas, such as urban areas. And with the global availability of smartphones, war crimes and human rights violations are increasingly being captured on camera and often instantly uploaded to social media. Forensic architecture can use audio and video analysis techniques combined with 3D computational modeling to recreate these crime scenes using the online media and provide new forms of evidence for prosecution teams to ensure that their perpetrators do not escape justice. However, the sheer volume of online media means that there's a big challenge to the investigation team to efficiently search and retrieve information for a case. So my job was to construct an automated classification system to flag up YouTube videos that may contain an object of interest. To do this, I would need to assess the readily available neural net image classifiers and choose the best ones to implement into a prototype platform. Then, I could search for new ways to generate training data that would be additionally required to improve these classifiers if necessary. So we chose as a test case to locate videos containing tanks. Tanks are a clear sign of escalating violence, and they may also indicate that a nation state is illegally involved in a regional conflict, since a local militia will not have the capabilities to support heavy armor. I first collated a data set, therefore, containing images of tanks. And you can see that some of them are pretty easily identifiable. We have a clear singular image centered in the middle of the screen there, whereas others are much less easy to identify. And this may be due to an obstructed or unexpected viewpoint, or they may suffer from motion blur. Now, typically, YouTube video contains a mixture of footage at this end, whereas the classifiers themselves have been trained on data that's more high quality at this end. So how do these classifiers perform? Well, actually, they already perform pretty well. I mean, they're able to sample 90 frames per second, and a huge high 90s percentage scores in accuracy, precision, and recall. And this was just for a generic database of a random sample of tanks. We can also visualize this performance if we take in all the information from our classifier and we cluster it and represent it on a graph. Now, basically, all of these data points now signify images. And the distance or the separation between them signifies whether they are images that are predicted to contain similar content. We know that these red images down here all contain tanks, and the rest of the images here in blue do not. So clearly, this algorithm is able to separate the red and the blue, and this is a sign of good, excellent performance. So, encouraged by this, I ended up building a programmable modular program that would take in a sample of YouTube frames, classify them, and then return that to a team of investigators that flagged up all of the videos that would contain a positive identification of tanks, as well as the position in the video at which this occurred, and also the confidence score of this classification. Now, this could be run locally, or could also be run in a purpose-built API on ASI's cloud-based data science platform, Sherlock ML. And applying this to a test case, an ongoing investigation, took in a YouTube search of 550 videos, which represent about 60 hours of footage, and it reduced it to just 2 hours of footage that was flagged for review by the investigation team. Now, this module can be changed, so you can identify a different object, or you can also implement different user-built classifiers if you wish in the future. But there's a question. How well is this actually performing on the YouTube videos themselves? Well, if we take a sample of them and we painstakingly label 4,000 of them, whether they do contain tanks or not, then we can see that actually there's a drop in performance. About a 15% drop in accuracy and recall, and from our clustering diagram before, we can see that the mixing of red and blue points is showing a lot of false negatives and false positives. Now, in practice, this means that there could be a lot of unnecessary workload for the forensic architecture investigation team, and also potential evidence could go missed. So how do we improve these classifiers? particularly in cases where we may not have access to large databases of training data. Now, this is where the really exciting stuff can happen in the future. Using forensic architecture's expertise in 3D design, we've created a pipeline that can generate synthetic data from simulated environments. And theoretically, when this is finalized, we can put any object of interest into any surroundings and generate a synthetic data set to then train or retrain for transfer learning the neural nets. Now, this is cutting-edge R&D stuff. So at the moment, what we're trying to do is use sophisticated ways to ensure that the synthetic data sets basically they will be able to then retrain neural nets to recognize real data sets and not introduce any unforeseen biases. So overall, my project allowed me to build a video classifier for forensic architecture and also explore the generation of synthetic data sets in order to train neural nets. But more than that, what it served was a prototype for a data science toolkit that could be used by open source investigation teams, allowing them to apply AI and machine learning to actively fight for social justice. Thank you.